So for lab on Monday, your pre-lab involves some calculations. It involves some dilution calculations, which we've done before, and I sent you a video on serial dilutions. These are not actually serial dilutions, they're just dilution calculations, so you're going to use that concentration of the concentrated times volume of the concentrated equals concentration of the diluted times volume of the diluted to do those calculations. But then we also have a weighted average calculation that you have to do. And so I thought I'd do a little review on weighted averages for you. So we use weighted averages a lot, right? All the atomic masses you see on the periodic table are weighted averages, right? So the element boron has two isotopes. Hopefully you've learned about isotopes in lecture, right? And the two main isotopes are boron 10, which has a mass of 10.0129 AMUs, atomic mass units, and boron 11, which has the mass of 11.00931 AMU, right? And you'll note that the 10.811 on the periodic table is not a straight average, right? If it was a straight average, then it would be somewhere around 10.5 AMUs, right? But it's not. It's reported as 10.811. And why is that? Right? So you'd see if it was a straight average, you'd get about 10.5, right? But it's not a straight average because the isotopes aren't present in equal amounts. It's not 50-50 boron 10, boron 11. Instead, there's 20% boron 10 and 80% boron 11. So when you take the average atomic mass over a big sample, it's going to be more heavily weighted towards boron 11 than it is boron 10, and you can see that in the average atomic mass. But how do we actually calculate a weighted average? So we know that this is the mass and what we call the percent abundance for boron 10, the mass and the percent abundance for boron 11. So to calculate a weighted average, you take the mass of the given isotope and you multiply that by the percent abundance in decimal form, right? So 20% is 0.2, right? And then you add the mass of boron 11 times its abundance, or 0.8, 80%. And when you do that, you get an overall weighted average of 10.81 AMU. Okay, so where else might you see weighted averages? In calculating grades, right? If you look at your syllabus, you will probably see that tests are worth something like 40% and quizzes are maybe worth 10%, lab is worth 12%, homework is worth 10, maybe participation is worth 8, and your final exam is worth 20%, right? So that's going to be a weighted average. You have lots of homework assignments over the course of the semester that are probably worth far more than 10 points total, right? But you're going to take that and you're going to weight it as 10% of your grade. So how do we actually do that? Well, in order to do that, right, if you know what your grade is for each of those components, you can calculate it in terms of a percentage, right? Then you can use that to calculate your grade in the class using this weighted average, right? So we see here, whoops, let's just start this. Here's my 40%, 0.4, right? That's the percent weighting. And then the 70 is the actual grade on the test. So that's going to be the contribution of my final grade that's going to come from my tests. And you can see how the rest of them follow, right? So quizzes, 10%, if I had an 80 on that. And if you added all of these things up, you'd find out that your total score was 80.2 out of 100. So that would be your final grade. Right. So the one thing you do have to do, right, so you can use this to calculate your grade in a course, but the one thing you have to do is you have to first calculate your score for each portion as a percent, right? So for your quizzes, how do you do that? Well, you add up all your quiz scores and divide by the total number of points, and that will give you your percent, right? So then what you really have to do in the pre-lab is to use weighted average to determine a percent composition. So in terms of atomic masses, again, if we think about that, the two most common isotopes of chlorine are chlorine 35 and 37, and I have their masses there. And from the periodic table, we know the average atomic mass for chlorine is 35.45. But what's the natural abundance of the chlorine 35 isotope? How do we figure that out? Well, if we say, well, let X be the percent abundance of chlorine 35, right? We know that the two isotopes together have to add up to 100%. So we can say let 1 minus X be the percent abundance of chlorine 37, right? Because when we add up our percentages, our decimal percentages, when you have 100%, you have 1, right? So then what we're going to do is we are just going to sub X and 1 minus X into our equation that we had before, right? So we have X, which is the percent abundance of chlorine 35 times the mass of chlorine 35, plus 1 minus X times the average mass of chlorine 37, and we know that the total average, weighted average, has to be 35.45, right? Then we got to do a little restructuring, right? So I just put the X after here. We need to distribute over the bracket. So 1 times 36, we get that. Negative X, we get negative this X. Then we're going to collect our like terms. So we collect our X's together and we put this number here over on the other side, right? Collect our numbers together. We end up with this relationship here. If we divide both sides by the negative 1.9970, then we find that X is 0.7591 or 75.91%. So we know that chlorine 35 is 75.91%. And then that means the chlorine 37 isotope makes up the rest to get to 100. Okay, so now that you understand weighted average a little bit better, hopefully, how does this apply to lab? Well, in pre-lab question 3, you have to calculate the amount, or the percent, reported as a decimal, of a sample that is actually malachite. If a student synthesized a product that they found out was 63.22% copper. So in your lab, you're given this table that tells you the 3 different compounds that could be in your sample and their percent coppers, right? We know that 63.22 is in between these. So it's higher than malachite but less than copper hydroxide. So that tells us that our product is most likely a mixture of these two. We're going to assume it's a mixture of just these two, right? So accordingly, we are then going to say, okay, well, let's assume that it's X percent malachite. So let X be the percent malachite, right? And then the rest of it is going to be the percent copper to hydroxide. Okay. And we also know that the total copper is 63.22, right? And in our other equation, our other example, we had masses of individual isotopes. In this case, we have percent copper, right? These are acting like the masses of the individual isotopes. So you should be able to put together now an equation and solve for X so you can figure out what the percent malachite is. All right, hope this helps. I'll see everybody on Monday.